us out. So last time I was trying to talk about this idea of AX equal to B. And solving over or under determined systems, you can't do it. You either have an infinite number of solutions or none. And yet you hit backslash and you get one. How did that work? You have to impose a constraint, right? So just remember, in generic data science, we do want to come back and solve this. And A is going to be oftentimes tall and skinny, short and fat. So overdetermined, there are no solutions. Underdetermined, infinite solutions. And yet I still hit backslash or I do something and I give you a solution. How does this work? How it works is just simply this. Two options, subject to. So when I'm in underdetermined case, I just simply say, all right, fine, there's an infinite number. Give me one that satisfies my subject to line. And oftentimes, the subject to line here is just give me the solution with the smallest L2 norm, or give me the solution with the smallest L1 norm. And this one here is going to be important for us and what we talk about, because it's going to promote sparsity. In other words, it's going to try to give you a solution where most of the values of x are 0. That's what the L1 norm does, which I totally didn't demonstrate for you last time because of the train wreck. But if you look at the notes, it's all there. Okay? All right. So this is if you're in this underdetermined case. Put under. If you're overdetermined, it's different. In an overdetermined case, hold on. Sorry. This is, yeah, okay, fine. So, okay. Let me come back to that. So this is one possibility of a constraint. The other possibility, if you're underdetermined, right, infinite number of solutions, okay, right? So then I pick one of these things to nail it down. If you're, sorry, that's overdetermined. If you're underdetermined, I can actually satisfy this thing here. And so what I want to do is give you a solution. And now the subject to line changes. So you can say, how about if I minimize one of these norms, 1 or 2. Subject to, my subject to line is x equals to b. Because I can satisfy it in that case. Right? So if underdetermined system, I can satisfy the equations. It's just that there's an infinite number of ways to do it. So I say, satisfy it. I don't know, give me something back to smallest L1 norm. Okay? If you're overdetermined, you can't satisfy it. So if you can't satisfy it, you just say like, well, how about I minimize that. It's supposed to be 0. It's not. But I can pick some different norms here, 1 or 2. So these are the sort of your two canonical cases. All right? So it's not, so one way to think about this is just optimization. I've written it this way, right? Minimize this or minimize that subject to. All of machine learning is an optimization. All of it. And there's so many different machine learning ways to do machine learning because we just pick out different things to optimize. Okay? So optimization is at the core of everything we would do around this. And it's also at the core of the minute you write this down with these types of equations, non-square matrices, you're optimizing. Okay? When you hit backslash, optimization is happening if it's not a square matrix. That's, I guess, my main point. Everybody okay with that? All right. Now, it is kind of nice, the backslash, right? Because it does give us a way to not have to think a little bit. And in many cases, the solution we get from the backslash for over and underdetermined is perfectly fine. I get a solution, I can use it, do things with it. But now we're starting to get to be, we're going to start doing things that are like more customized. We want to start thinking a little bit about the solutions that we're getting out. Okay? And when we start really thinking about it, it starts making us think about, oh, what's the optimization I should be doing associated with that? So I'm going to give you an example today. And it's really related to that L1 norm that I was trying to promote last time, which promotes sparsity, trying to make things 0. And here's what I want to do. I want to take a signal, F. There's F as a function of t. And of course, this is going to be a bunch of discrete points. I'm going to be able to measure F every delta t for a bit of time. Okay? So it's a vector. Now, here's the question that comes about. And this is an important concept related to this. Do you know what this actually is? This is just a compressor and a decompressor of information. Part of the reason all this technology works is because every single picture you take gets compressed in here. Okay? This is why you can just take all the pictures you want. Okay? When I grew up, we had to actually develop the film. So you thought very carefully, I don't want that. No. Can you fix your hair up before I take the picture? Because I'm not going to take one, because it's going to cost me to develop this. It's not like I can take 5 to make sure I get the one, right? I get one picture, I make it count because it costs money to develop film. Okay? Now you like picture, picture, picture. But you know why we can do that is because when it gets in here, it gets compressed. Signals are compressed. Audio is compressed. Video is compressed. And then what happens is it comes in uncompressed, and then when you want to actually look at it, it uncompresses it on the fly. So JPEG, which is a lot of images, it's a format. It's a compression format. So you take your picture, and in pixel space, it's massive. But in wavelet space, it's very small. Okay? So it's really interesting, right? Because this camera, it's an HD. So not even that long ago, we didn't have such high quality. But now it's got like 2,000 pixels by 1,000. I don't know. It's like 1,800 by 2,400, right? Pretty soon they're going to have 4K cameras in here. And then 8K. Do you know how many in the 4K picture? It's like 24 million pixels. Because it's an RGB cube. Do you know how heavy your phone gets when you start loading phones in there? It's 24. It's so much data. People are going to, so heavy. Right there. Okay. So you don't store that. There's a space in which you store the images, which is wavelet space. That's what JPEG does. Okay? So the whole idea of compressive sensing, and this is what we're going to go after today, is going to be making use of this idea of compression. So here's the idea. There exists a basis where I can take that signal and compress it. An abstract way to represent that is F, the vector, phi c. So these are my bases. And what C is the loadings or coefficients of the basis elements. Does that make sense? So there's a basis I want to put this in to represent the signal. So for instance, if I draw something like this, you might say, hey, I could probably put that in a Fourier basis. Looks a little oscillatory. In fact, it is. We'll do an example here. A lot of audio signals have a lot of oscillatory components. And so you can say, I could just transform my signal into Fourier domain, right? Everybody done a Fourier transform? Well, if you haven't, it's super easy, FFT. And now you're in a frequency domain. But what's kind of remarkable about most signals, if I put them in the Fourier domain, it's massively compressed. Notice here's what it looks like in time. And a signal like this in a frequency domain might look something like this. It's mostly zeros, a few non-zero elements. So the idea behind compression is to say like, oh, well, I could represent that signal, throw all these away, so I just keep these coefficients, these. Done. So when you want it reconstructed, I just give the, oh, here are the 4 non-zero coefficients. I can build the whole signal back out. Okay? This is my compression space. So audio would get put into this Fourier domain, and all I save is this. I save like 1% of the data instead of the actual time trace. And then when you want to hear it, I say, okay, I can build that back for you because I know what it looks like in frequency domain, build it. Okay? So that's the idea of compression. Now think about this. I'm going to take a picture. What's the first thing I'm going to do? If I take a 4K picture with 24 million pixels, the first thing I'm going to do is going to throw away most of the information. Do you know why? Because I'm going to take the picture. It's going to be 24 million pixels. It's massive. It's going to say, okay, let me go put it in the wavelet domain. I'm going to save about 1%, throw away 99% of that data. Right? So the first thing it does is throws most of your data in the trash. And it can, because most of it is either 0 or near 0, almost 0. So you just throw it away. Okay? There's some lossless compression formats. Have you heard of this? Right? Versus just compression. Compression always throws a little bit away, right? But it just shrinks your data. So the idea of compressive sensing is the following. Oh, so if you're going to throw 99% of my data away to begin with, what if I just collected the right information to begin with? Instead of collecting all this information, I collect just what you need to represent that. Does that make sense? I'm not going to throw everything away. Instead, I'm going to come in and say, like, I know this thing I'm taking a picture of, or this audio signal, I know I can represent with only 1% of the information. How about if I just go after that 1%? Okay, to begin with. That's compressive sensing. I'm going to take a small number of measurements from this and to be able to reconstruct the entire thing. Okay, how does it work? First, step 1, I have a basis, wavelets, or Fourier. I give it a basis set in which the signal is compressible. Okay, wavelets and Fourier is super easy to work with. We're going to work with Fourier today. What does it mean compressible? It means this matrix C here, or sorry, the vector C, which tells me how it's loaded. The vector C is mostly zeros, and like for instance, even this signal here, look, there's like, let's just say there's 4 non-zero components. It would mean that if I look at the values of C, it'd have 4 non-zero components. Everything else is 0. Okay? So notice C times this, it's basically selecting a set of columns of the Fourier modes. Right? Because it's all zeros, right? And these are like the cosine 0x, cosine 1x, cosine 2, sorry, t, cosine nt coefficients in there. So it just says, oh, I can throw most of them away. There's just a few I need. Which few? Wherever C is non-zero. Okay? So you have this, step 1. There exists a basis in which my signal is compressible. Okay? Step 2. I actually take massive subsample of that signal. So the way I'm going to represent this is B is phi f. So F, remember, is my signal. This is a vector of components. It's that. And I'm going to massively subsample it. So what I could do is I could make a sampling matrix. That's phi. So it has to be the same size. I'm going to have, like, say, p samples. And the non-zero components is going to tell me where to sample here. So for instance, I could sample here, and here, and here, and here. So if these are the 4 sampling positions, I multiply these together, it means I'm going to sample this guy, somewhere down here, and over here. Does that make sense? Everything else is 0. These are 1s. So that's a 1. Everything else is 0 there. So this tells me the actual points I'm going to sample my signal. Now, right away, you may be perturbed. If you come from an electrical engineering background or signal processing background, there's this thing called Shannon Nyquist. Has anybody heard this? How fast do you have to sample to resolve a signal? Twice the highest frequency. Why is that? So let's talk about Shannon Nyquist. Suppose I wanted to resolve that signal. How fast would I have to sample? Shannon Nyquist says, well, you have to, like, at least do that. So that's twice the highest frequency, essentially. Why? Because I have to, like, see it go up and down. Everybody okay with that? Does that make sense? All right. Have that picture? Let me move over one board. So it's easy for you guys, but people at home are panning on that camera, and they can't see it all at once. They're getting less education than you. Okay? Look what I just did. Like, I drew this. I have a sample here and here. Shannon Nyquist would say, you got no shot at getting this. See all that stuff, structure there? I didn't sample it. How am I going to get that out? How am I going to reconstruct that signal? Okay? It's a problem. So there is an assumption, however, about Shannon Nyquist. So this is sort of, in some sense, the idea of what we're going to do. And I'm going to show you. Totally going to nail that. It's like magic. Okay? But it also starts to work around this dogma. The dogma here being, no, no, no. You cannot resolve that fast of an oscillation if you don't sample that fast. Okay? Now, so what gives? What's going on with this that compressive sensing is going to allow us to work this? Well, here's the thing. There's one, remember, constraints and assumptions? Constraints and assumptions are really important things in everything we do. And here is the assumption that we haven't talked about, but the assumption over there that I already made. Shannon Nyquist assumes that you basically have a broadband signal. In other words, this is the highest frequency, and I might have all frequencies in between, so my signal is whatever. Goes from negative omega to omega and includes, this is your highest frequency, so it says all the frequencies are present. And if that's the case, you're never going to be able to beat Shannon Nyquist. So it's typically the assumption they don't tell you. Shannon Nyquist, when it's stated, is just like, oh, you have to sample it, twice the highest frequency. There's a caveat there, and the caveat is the assumption being that I have broadband signal. What's our assumption? Our assumption is that the signal is compressible. There's a few frequencies that matter. This has huge impact. I'm going to take a small number of measurements, and I'm not trying to recreate a broadband signal. I'm trying to recreate a signal that has sparse representation. That's the whole thing that allows this thing to happen. Okay? All right. Questions before we do magic? No? Okay, I mean, we're going to try to do magic and hopefully not crash a train. It's going to be awesome. I'm glad you came. Maybe you're the good luck charm for today for workout. We'll see. All right. Yeah.
Just to confirm, so I'm not familiar with Shannon Nyquist, but you have to sample twice the highest frequency. So that example, so it's just like the peak and the.
Yeah, exactly. So you know, if you're going to get this structure, you have to see it like go up and down. In other words, in contrast, what if I had sampled here and here? Do you think I could get it? I can't. How am I going to get everything in between? So this is often called aliasing. So if you don't get it right, it says, I don't see any of that. What it will see is something that's like, oh, it's something like that. Totally different frequency. That's aliasing. So the way is, if you don't sample at the right rate, aliasing. You get the wrong thing back. Okay? So this has always set a limit for sensors and detectors. Like I have to be up there at the Shannon Nyquist rate to get the frequencies I want. If I want to resolve frequencies at this level, I have to sample at a certain level. Otherwise, everything higher frequency is aliased. But of course, most signals are in fact compressible, and we're going to exploit that. So I made two assumptions. Step one, my signal has a basis in which it's compressible. So this C vector is sparse, mostly zeros. This is telling me there's a sampling matrix times the function. So if I do this, this gives me a small vector. This is essentially my massive subsample vector. So I take a small number of points, which is a portion of the signal f. Okay, ready for some linear algebra magic? Then I was trying to make all this big case to you that it's just ax equal to b. You ready for ax equal to b? Me too. Thank you for saying yes. Here it is. Ready? I have a signal. Actually, here's my measurement. My measurement, which is a small set of measurements of the full signal. There's my measurement matrix. Tells me which one's measuring. F. But what's F? F can be represented like this. So this is this matrix like this. This is this basis matrix. Vector C. These two can be my matrix A. So B is equal to AC. So this is like my X equal to B. What do we know about solution X I'm trying to solve for? Sparse. Okay, so all I want to do is say, oh, solve this subject to C being L1. So in other words, I can construct my sampling matrix, multiply it by my basis to get A. Here are my measurement locations, and you say, find the signal for me. So I just say solve Ax equal to B subject to this, because I know this is sparse. Once I have C, then it's easy. Once I have C, I can reconstruct my full signal F right there. Find C, Ax equal to B. That's all I'm solving. Okay, just keep that in mind. Just Ax equal to B, subject to. And my subject to line, my whole point of the lecture on Monday was supposed to be that if you use an L1 norm, you get sparse solutions, which is exactly what I'm looking for. Okay? Let's program. Okay, here's some wood. I didn't do that last time, maybe it'll work. That's like fake wood, I think, so I have to really, I'm glad there's something here for me to knock on. All right. So, let's build the signal, let's do the compression, and we will see how this all works out. We do this. All right. Pull my screen up. Here we go. Okay. Here we go. Let's start programming. So I'm going to make a signal. And what this is, actually, let's go to do time is going to be linear space, 0 to an eighth in n points. And I'm going to make, this is the the A tone on a dial tone. So if you have your phone, if you push the A, you know, do, do, do. Okay, that was awesome sound. Did you hear that? I just made a phone sound. Well, my phone sound, the A, is this signal here. This is actually the A. So what it is, it's a combination of sine of 1394 times pi times t, okay, plus sine 3266 times pi times t. That's the A tone on a phone. Okay? Let's plot it. It's basically a beating between two frequencies. Okay? So if I run this, you see it? All right. So that's a lot of data, and it's for 1/8 of a second. So let's zoom in here. No, not rotate, zoom. And just look at it. Right? It's beating at two frequencies. There it is. Their A tone. Okay, so first of all, that A tone is two frequencies. So when I represent it in the Fourier domain, it's how many frequencies? Two, right? Essentially, this is what I put in. But of course, I'm going to FFT it and look at this in the frequency domain. And let's just see what it looks like. Because the domain of 1/8 of a second has its own Fourier modes, which don't necessarily match the frequencies I have here. Okay, so let's do that plus like a line width 2, because it doesn't look that good right now. All right. Now, I can find the FFT of this, which is FT. I'm going to actually do the discrete cosine transform of F. Okay? And then I can plot FT. And let's do figure 2. So I'm going to put it in cosine basis. Okay, there you go. That signal, you Fourier transform it, and as advertised, it's two frequencies, and it's not quite two frequencies because, in fact, the frequencies I put in for the A tone don't actually match the cosine frequencies that fit in 1/8 of a second, but they're close. So let's just zoom in on these two frequencies. Here they are. They're mostly two frequencies. Okay, everybody agree with that? So you could see that when I take this thing, because I have 5,000 points, so here's the artificial thing about that. When I write down a signal, draw it, and I sample it, how many measurements I have, that's the number of Fourier modes, regardless of the intrinsic rank of the dynamics. Remember, when you're doing PCA type things, right, you guys have been working on this, eigenphase, there's like an intrinsic rank to things. What's the rank? Well, here, the rank is just how many points I picked, right? If I say there's 20 million points, it has to say, okay, if you're going to do a discrete cosine transform, it's going to give me 20 million Fourier modes. It's two frequencies. It doesn't matter. It's how many points you have that determines the number of Fourier modes. But it's two, okay? So in other words, this is the number of Fourier modes I actually used here is totally artificial. And what I really want is there's some low rank structure, these two modes. I want to capitalize on them. Okay? That's what makes this thing here sparse. It's dominated by a few non-zero components. Those right there that I'm showing you. Okay? Everybody good with that? All right. So far, so good. Everything's working. 10 lines in. Whew. All right. All right. I'm a little shy on the computer right now. I'm not feeling, you know, my confidence was shaken. Gotta get back on the horse. All right. So let's start subsampling. Okay, so what I've just showed you is a signal and its Fourier representation. Fine. By the way, most signals aren't that sparse, okay? But most signals are pretty sparse. So let's just leave it at that. So now what I'm going to do unlike my notes a little bit, I'm going to take 500 samples. Okay? So how am I going to do it? Well, I'm going to make a measurement matrix, and I'm going to do you remember the rand perm command? Yeah, I used it before. Okay. So what I'm going to do is say, let's call this XR, rand perm. Actually, let's call this just temp. It's just some temp variable. Rand perm 5,000. So what rand perm 5,000 is going to do is going to take numbers from 1 to 5,000, shuffle it randomly. Okay? And what I'm using these 5,000 for is to tell me the points I'm going to measure. So what I'm going to do is say, all right, we've got a random thing, so let's call it XR. XR is going to be equal to, what it's going to be equal to is the first temp, the first 500 components of temp. So I shuffled it, and I say, okay, go grab the first, now that it's shuffled, go grab the first 500, and it's going to tell me the measurement locations. So what I'm going to do with this is go back to figure 1. Okay. Actually, I'm going to do something more. I'm going to make the variable FR. And here's what FR is going to be. FR is going to be this. Shoot, I should call this TR, not X. So this is the T locations. TR, these are my... See what I do with that? I said, okay, take those points, plot them, too. And I'm going to go back to figure 1, and I'm going to say, hold on to what I had before, and now I'm going to plot TR, FR in red circles, line width 2. And what you're going to see is these are going to be my measurement locations. What was that? Oh, yeah. Good. Thank you. Awesome. Thank you. All right. Oop. All right. So let's see here. Oh, I see. Hold on. Okay. I see. TR, okay. Let's call this ends. What I want is TR is T at the indices, and FR is at TR. Okay. All right. There we go. Here we go. Now let's just go ahead and look here. These are all the measurement locations of that signal. So instead of 5,000 locations, I have 500. Let's go see what this looks like. There. Random measurements locations. Okay? So, a couple things to note. That's where I'm going to measure, and I'm going to ask the following thing. This is my magic for today. Given the red, measurements, reconstruct in blue. Now, what should be immediately challenging looking is that some of it you look like you could probably do. Some of it is kind of like, seriously, you can do that? Which is, take a look right there. See these two measurements? I have one here, here. How's it going to know that that happened? Nyquist would say to you, you don't know, you're going to be screwed. Compressive Sensing is going to say, yeah, well, we're changing the paradigm, baby. Why? Because I know that that signal is compressible on a basis. So I'm not looking for all frequencies. I'm just looking for which small number of frequencies are consistent with all the data. Pull those out, reconstruct everything in those. And then I'm going to go all the way down to, so this still looks like, okay, maybe you could believe I can do it, maybe not, but you know, it's maybe a stretch. Maybe I wouldn't do a very good job. Then I'm going to go to this. Let's go zoom in. And then you're going to be thinking that maybe this is really stretching it more and more. Maybe I'm going to be lying to you because it looks harder and harder to do, because look at these stretches here that I got to fill in. and I only have a measurement here and here. How do I know that signal turned 3 times? I never took any measurements in there. Can you really do that? Okay? All right. Everybody clear what the task is? I give you measurements, the red balls. You build the blue. You rebuild the whole signal for me. Okay? All right. Okay, with that stated, and with us still moving along without derailments yet, we're gonna keep going. Now, what I need to do is I need to figure out how to build. I know where I want to measure now, and I know I want to represent it in the Fourier domain. So I want to understand how generically I could take any signal, like a delta function, and put it into the Fourier domain. That's going to figure out my mapping over from frequency space to time space. So, okay, I'm going to make a matrix D, which is going to be a DCT of I n by n. Okay? What am I building? Building this. This is a matrix. It tells me I've got 5,000 components. I've got 5,000 Fourier modes. I know that I'm not going to use them all. I know I'm going to use only a few of them, but I still have to have that basis. So I set up the basis. That's how I set it up. Okay? So remember, here's the picture I want to show you. This is the cartoon. Here's the basis. It's big. There, all these the basis elements are determined by the number of points I have. Okay? And then I have my, here's where I'm going to measure. So I'm going to build a measurement matrix. So I have this times this, and then I can do the regression. And I'm going to find the C vector. Okay? So I'm just building that. Okay? That's done through the discrete cosine transform because that's, in fact, the basis I'm going to use. And when I measure it, when I multiply by phi, in other words, phi is going to tell me where am I measuring this. Okay, so I'm going to make a matrix A, which is D, and it's at the locations end. Okay, these two moves are really important. Let me go back to the board. Sorry, I should have just stayed up there. I just did this multiplication. What does this matrix do? It pulls out certain columns of this, right? So like remember this. This is going to take a measurement matrix. It's going to say I'm going to actually subsample this massively at these locations. So there's only certain rows that matter. Or sorry, certain columns that matter out of that matrix. The phi matrix. In other words, it's going to say, hey, here's what you're measuring. Here are the things that matter. So wherever you pick to measure, that's the only place it can sample the Fourier modes. Okay? So it's looking across the Fourier modes. So when I do this, it says, all right, you just built the basis, but I only get to sample it here. At these locations. That's where you're taking the measurements. Okay? Remember, end was just some random locations. Okay? I do that, you get this. Okay. Everybody good with that? That's setting up everything I want for us to go forward. That is my matrix A, and that's why I called it A. And all I said I was going to do today was solve AX equal to B. Okay? By the way, I actually am really serious about this. Do not, don't ever discount what AX equal to B can get for you. A lot of people want to get fancy with math. Oh, I got it super sophisticated. No. AX equal to B will solve 95% of your problems. Okay? Just have that in mind. Don't be all like uppity about your math. Like, well, it's too low for me. I got to be doing really advanced things. AX equal to B is advanced, and it's hard. Most people don't. Myself included. I'm not saying if I could rip on my younger self, I totally would and say, dude, you need help. You need to know more Ax equal to B. And my younger self, no, I know it all, especially when I was 18. Remember when that was awesome, when you knew everything? It's only gone downhill since. But anyway, Ax equal to B. It's kind of it. So now, let's start doing this. So my structure is over there. It says I take a sampling of my real signal. What is that? The sampling of my real signal is FR. That's where I sampled it. Those are the red dots. Right? What does it say? B is equal, I wrote it over there. B is equal to AC. So I have, right here's B. Okay? And if I want to find my signal, the C vector, let's call that actually X, is equal to pseudo-inverse A times FR, and I have to transpose that. This is one way to solve it, least square fit. I subsample, do least squares. Okay? And what I just got out were a bunch of coefficients. And once I have those coefficients, I can get my signal back just by projecting them onto the Fourier modes. So what I'm doing right now as a first step, I'm not even going to do sparsity yet. I'm just going to say, I have Ax equal to B. What if I just solved it with the backslash or a pseudo-inverse? What would I get? Okay? So I have that. That's what I just did there. I just get back to my signal. And then compare my signal to what it actually is. Remember with that? Okay. So I'm going to call this, so that's X, and my signal from it, let's call it signal 1, is the DCT of this X. So now I can do, I'm on figure 1 right now. So what I'm going to do is the following. Actually, I'm going to make a new figure, figure 3. I'm going to plot the original signal, right, which is T versus F, right? And let's make that a blue. And now I'm going to actually I'll just, and then also we'll plot T versus sig. Okay? Sigma 1, yeah, sorry. All right. So if I did this and I said, okay, I subsampled, I did a least square regression, least square fit, how well did I do? Not terribly well. The orange is my approximation to the blue. And in fact, this helps reflect something for you, which again, how you solve Ax with B really matters. It's not all methods are the same, and you can see here, you would throw away this method and you say like, okay, clearly this is a stupid thing to do. It doesn't give me anything like what I'm supposed to be getting. What did the least square fit actually do, or P pseudo-inverse? It did a least square fit. So when it tried to solve for the frequencies, do you want to see what it did? Let's talk about what it did. How does least square fit win? Make everything really small. So what it did in the frequency domain is it made everything really small. So let's go figure 4. Figure 4. What I'm going to plot now is the original signal, right? The Fourier transform of the original signal. Where is it? F T, right? Okay. And we'll plot that in blue. And then now we'll also plot. So those are the Fourier coefficients. And here's what this pseudo-inverse thinks the coefficients are. X. Right? That's from here. That's what it solved for.
So in line 26, is that not the inverse transform?
Actually, I think it might be. It doesn't actually matter. Forward and backwards on the DCT doesn't matter. Yeah, right. For the FFT, it's I and minus I. It doesn't really matter so much. All right. red is pseudo-inverse. What did it try to do? What did I tell you it was going to try to do? Make everybody super small. See, it did it. It got the best least square possible. And it said, your signal is made up of all of these Fourier components. It does not want to load anything up like this because it has to square that. That's its error. And it says, I'll make everybody as small as possible. Least square wins. It gives me crap fit. It doesn't give me anything that looks like the spectrum. It says, in fact, it's super broadband. All frequencies matter. They don't. Okay? So now let's do L1. Okay, this is where I'm going to have to last. So you see how I saved the train wreck to the end? Because if I really wreck at the train and go, oh, we're out of time. You won't see the death. You'll just go home. Like, did he die? I don't know. It was a cliffhanger of an ending, and I'm not sure he died. It's like, okay, so now we're going to replace this here. And let's just actually, in my notes, I do a comparison of all of them. Let's instead do the following. I'm going to do CVX, begin. This is the convex optimization program. And what I'm going to do now is a variable. I'm going to solve for that x again, size n. Okay. Tab it in. All right. So there's variable x. Minimize the norm of x subject to the 1 norm. Oh, sorry. Minimize the norm subject to a times x equals to that fr cvx n. Okay? So I go and solve this thing. I say, go ahead, minimize the solution with the norm. It satisfies the conditions because it's massively underdetermined. So I know I can satisfy it, but give me the L1 norm. And then, once I get it, plot it, same as before. Takes a little bit longer. Okay, so let's go look. Hold on, where's my, did it complain? Figure 3, yes, it complained. X, hold on. See, this is where, I don't know what's going on. See, here we go, here we go. Let's go look here again. This should be fine, right? X, okay. Oh, you know, I got to do this again. Doggone it. I don't know why I did this yesterday. Remember that? This is how the train wreck kind of started. Is everybody nervous? Do you feel like you're going to go hit a wall right now? Me too. All right. Okay, now it's working because it's taking a while. Because now it's actually doing an L1 optimization problem. See, it's like blah, 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 blah. It's trying to find that solution. So now it's actually explicitly doing L1 optimization. Hey, by the way, why do people like L2 and backslash and pseudo inverses? They're wicked fast. Essentially, if you want the least square fit, trivial. Super fast, it'll get the solution to you immediately. Okay, we've optimized the hell out of L2 because we've been using L2 since the time of, Pythagoras, but also even algorithmically when you have Gauss and these guys, they're already committing to L2. And when people start committing to L2, you start thinking about algorithms, how do you compute these things? And so we've been thinking about that for a long time. People are thinking very hard about L1 right now. And you see progress in optimization routines that go faster and faster. But L1 is slow. Hold on to it. Hold on. Hold on. We're going to get there. Come on. Come on. Just pretend I'm really talking about important things right now. You're on every word I'm saying. Yeah.
Does this work the same way if it's used complex?
Yeah. So you can do this in a complex domain. I think in CVX you have to break it up into a real imaginary part and do it that way. So yeah.
So since we randomly permuted the rows of A, we didn't just select rows, we also randomly permuted them. But then pseudo-inverse sort of unpermutes them in some sense. Does that permutation of the rows you select matter in the L1 norm?
No,
Or is it
so
just
I
in
just did the
L2 norm?
subselection, and I know how to project back. Okay, here we go. Oh, dudes, we got it, I think. Hold on. Check it out. Red is my solution. Blue is the original. Dudes, you see it? Nailed it. It went for a sparse solution. Let's go look at the reconstruction, and you can already see stuck the landing. Okay, awesome. Okay, here's your job. Everybody home? The code's right there. This is a really important example. Notice what I did. This is like magic. I know you guys are never impressed with anything I'm doing up here, but they're like, I'm doing magic shows all the time. Like I could pull like a unicorn out of that wall and you'd be like, oh, okay. But check it out. Take this thing. I did 500 measurements. Go to 200. It's amazing. Like when I first saw this, I was like, I got to teach this because this is like magic. This is just math with a constraint, and it allows you to do things you didn't think possible. It's telling you if I massively subsample in my measurement space, it's not like I have no hope. I have hope because if I know there's a compressible basis, I can massively subsample an experiment and still build the whole thing out. Many of you are in that situation with your real data. If you have real data, you don't get measurements of everything. That's bull. Okay? This is a helpful way for you. Okay, sweet. See you guys Friday.